So in this lecture, we are going to study the global value numbering optimization, or GVN. So it is one of the most important optimization in the C compilation. And let's study what's going on there. So it is about homework 5, and you're going to implement GVN on the KCC compiler. And GVN's motivation is removing obviously redundant computations. For example, you have two instructions that is computing 1 plus 2. You compute 1 plus 2 once, and then later you're going to compute 1 plus 2. Then they are obviously redundant because they have the same structure in the computation. So we are going to replace the later one with an earlier one. That's the motivation of this global value numbering. And the idea here is that we are going to classify syntactically equivalent computations into the same class. So here we are saying we are numbering instructions, and we are numbering equivalent instructions into the same numbers. And then we are going to replace an instruction with a number with another instruction with the same number. So that's the reason why this optimization is called value numbering. And the reason why it is called global value numbering is we are going to look at all the blocks in the same function at the same time. So local value numbering, on the other hand, is looking at only one block, but global value numbering is looking at all the instructions inside a function. So that's the difference. So here the challenge is that, okay, suppose that we already syntactically classified instructions into numbers or equivalent classes. But it is not always safe to replace an instruction with another. For example, if you have two instructions in a row, but you cannot replace an earlier instruction with a later instruction because because the later value may not be defined when the earlier value is used. So you have to somehow deduce when it is safe to replace an instruction with another. So this is basically a domination relation. If you want to replace, for example, A with B, you need to make sure that B actually dominates A. And we need to use such information, the domination relation information, for the instructions of the same number, basically. And the idea here is that we're going to maintain what is called the leader values for each number, for each program counter or line number inside of program. And the leader value is a value that can be used inside at the program counter as the replacement for the given number. So if your instruction is numbered, for example, 11, and your leader value for the number 11 is, for example, %v, then your new instruction can be replaced with %v. So that is basically what is meant to be the meaning of this leader value. So, okay, this is the high-level description of the algorithm, and we are going to look at the details one by one. But before that, I would like you to read the KCC's compiler's repository, and you can test your implementation of GVN by doing this. Cargo test examples GVN. Then you're going to execute your GVN optimization for the given input-output files, and it is going to check if your optimization is producing an expected output of the optimization. So look at the examples here. This directory contains both input and output files of this GVN, and please see what's going on there. So you're going to submit your optimization in this gg.kaistatus.kr, but it is going to be announced later. So for the time being, please test your GVN optimization using this script. If it says OK, then you're going to get the 100% credit for this optimization homework. If it doesn't work, then you're going to get a 0 point for this homework. It's a simple grading scheme, basically. Okay, let's explain this global value numbering with examples, because always examples are the best way to learn something. But as I said, a global value numbering is a generalization of a local value numbering. So we're going to look at the local value numbering first. So suppose we have only one block here, and here we are going to compute 4 instructions. First of all, we're going to calculate a plus 37, provided that a is an argument to the function, and it is going to be x1. And later, we're going to compute x1 plus 42, and let's say it is y1. And here, an important thing happens. We are again computing a plus 37 and name it x plus 2. X2. And this, as name suggests, you can immediately see that x1 and x2 should have the same value. And furthermore, we are going to calculate x2 plus 42, and let's name it y2. And again, you can immediately see that y1 and y2 should have the same value because x1 and x2 have the same value, and we are going to add the same value to the same values to get y1 and y2. So as a result, after some value numbering optimization, we want to just remove these instructions. So x2 is no longer needed to be computed. Y2 is also no longer needed to be computed. So it is going to be replaced with a nope, which does nothing. And we're going to replace x2 with x1 whenever x2 is used in the remaining code of this function. X2 is replaced with x1 because x1 and x2 have the same value. And y2, which will appear in the rest of this block, will be replaced with y1. Why? Because y1 and y2 should have the same value. So this is basically the motivation and the most basic example of what's going on this value numbering. And I would like to explain the algorithms in more details. So as I said, we are going to assign the same number to equivalent computations. So here is the colors, and the numbers are basically the unique numbers. So at the beginning, we are going to give A the number 1. Oh, here, let's say that the circled numbers are all numbers, and these plain numbers are all constants. So these are expressions, and the circled numbers are numbers. So we are going to assign numbers to each expression, which can either be constant or registers or some computation. And here at the beginning, we are going to assign the variable a, which is assumed to be an argument with the number 1, because it is the first variable to consider in the optimization. So it is the number 1. So far so good. And looking at the first line of this code, we are computing a plus 37, right? And a is meant to be the number 1, and 37 is a constant, so you don't need to explicitly give a number to this constant. Constant is just constant. There is no need to explicitly reason about this value. So we are going to say, oh, we are adding a value of number 1 plus 37. And this is happening here. So we analyze that. And we're going to say that, oh, this is the new pattern which hadn't appeared so far. So we're going to give a new number to this expression. Number 1 plus constant 37 is now called number 2. It's a new number. We don't know yet what is the exact value of this, but let's say that it is a number 1 value plus 37. And now we know that a plus 37 is number 2, and this is assigned to x1, so we are going to give x1 the number 2 again. So this is what's happened. These two are what is added to our knowledge about the values of these expressions and variables after the first line. Okay, so far so good. And let's move on to the second line. And we're going to add x1 plus 42. And we consider that x1 is actually number 2 here. So we are effectively computing a value with number 2 plus a constant 42. And this is a new pattern. No, such a pattern hadn't appeared so far. So we are going to give a new number. Let's say it is number 3. And number 2 value plus constant 42 it will be number 3. And this computation is assigned to a y1. And as a result, y1 will also have a number 3 value. So after that, we are going to compute a plus 37, and we can see that a is number 1 here, and we are going to compute number 1 plus constant 37, and it is number 2 according to the knowledge database we collected so far. Oh, so we can immediately conclude that this x2 is number 2. And similarly, this x2 is number 2, and 42 is a constant 42, and the summation of these two is number 3, and as a result, y2 should be numbered with number 3. So this is basically the internal working of the GVN optimization for this example. So far so good. And we can immediately say that the variables and expressions of the same number should have the same value. For example, this x1 and x2 have the same number. And as a result, they have a syntactically equivalent operations, and they should have the same value. Similarly, y1 and y2 have the syntactically equivalent operations, and as a result, they should have the same number, for example, 3 in this case. Now, until here, we analyze this code, and after that, we are going to actually transform the given input program using these analysis results. So the basic idea here is that we're going to replace a later value with an earlier one with the same number. As a result, x2 should be replaced with x1, and y2 should be replaced with y1 because they have the same number respectively. Okay, so it is quite simple. It is quite straightforward. And after removing these two instructions, we're going to replace x2 with x1 in the remaining of the code, as I explained just before. It is quite straightforward, and it's for this example, and it is particularly because there's no complex control flow. Everything is just inside the same block. So so it is really easy to say, oh, y2 is a later instruction and y1 is an earlier instruction. So we need to replace y2 with y1, a later instruction with earlier instruction. But what if we have a little bit complex control flow graph? What if we have loops? What if we have branches? And now we are going to answer this question in the remaining of the this video. So in the absence of such complex control flow graph, and value numbering is essentially explained to the details here. So it is really easy to implement such an algorithm in the absence of this control flow graph complexities. So in the remaining of this section, we are going to explain such complexity and how to deal with it. So the second example is illustrating why such complex control flow graph is complicating the matters here. And here we are going to see an example with 4 blocks. So at the beginning of the function b0, we're going to non-deterministically branch to b1 or b2. So this undef is a non-deterministic value, and we either go to b1 and b2, and we don't know yet. So it is only decided at the execution of this program. So in the block 1, we are going to calculate some summation, 42 plus 37, and assign it to a register here. And we're going to go to the last block, which is called B3. On the other end, in B2, we do nothing and immediately jump to B3 here. And let's say we're going to calculate the same thing as before here, 42 plus 37, and assign it to register here. And we're actually going to use it. So this B3's I0 is used as an argument in this function call. And you can now immediately see that, oh, this B1's I0 and B3's I0 should have the same value because by using the analysis we did for the previous example, by numbering the syntactically equivalent expressions to the same number, we can see that, oh, this B1's I0 and B3's I0 should have the same value. They have the syntactically equivalent computation, and as a result, they should have the same value. But the problem here is that we should not replace this B3's I0 with B1's I0. The reason is, it may be possible that the counter flows from B0 to B2 to B3. And if it is the case, this B1's I0 is never defined so far. So when this B3's I0 is replaced with B1's I0, then it is an ill-defined, it is a ill-typed program, because when the control flows from B0 to B2 to B3, B1's I0 is not defined in this execution. So in this program, we should never replace this B3's I0 with B1's I0. And more generally, we can replace A with B of the same number only if A is dominated by B, or equivalently, B dominates A. Only if the B dominates A, we can replace A with B. Here, this B1 I0 doesn't dominate B3's I0, and as a result, this B3's I0 cannot be replaced with B1's I0. So here is basically this example is basically illustrating why I need to care about the domination relation and complex control flow graphs in the replacement of this global value numbering optimization. And I'd like to introduce another example, which is a little bit complicating what's going on in the global value numbering. So we sometimes, when it is beneficial, we want to insert a phinodes to reduce the number of computations. So here's an example. So in this example, again, we non-deterministically jump to B1 and B2 from the initial block B0, and in the B1, we are going to calculate 42 plus 37. And in the B2, we are going to compute the same thing, 42 plus 37. And in B3, again, we are going to compute the same thing, 42 plus 37. So from B0, it is either jumping to B1 or B2, and in both B1 and B2, it is computing the same thing, and in both blocks, it is immediately jumping to B3. And here it is going to compute the same thing. Again, there are a lot of redundancies here, but you can see that no register is dominating another among these three. So for example, B1's I0 doesn't dominate B3's I0 because of the existence of this B2. Similarly, B2's I0 doesn't dominate B3's I0. And as a result, we cannot replace this B3's I0 with either of these two registers. But you can see that there are some obvious redundant computation, 42 plus 37. So in order to reduce the computations, even in this case, there's an idea which is inserting a phinode that is collecting this computation at the beginning of this B3. So it is going to be done in this way. So instead of computing again, we're going to introduce a phinode. Here it is called B3's P0, and it is either B1's I0 or B2's I0, depending on the control flows. If B1 jumps to B3, then B1's I0 becomes the value of this B3's P0. Otherwise, if the control flows from B2 to B3, then B2's I0 is becoming the value of this B3's P0. And you can see that everything is the same. It is 42 plus 37, 42 plus 37. This is 42 plus 37, and this is 42 plus 37. So regardless of whether, regardless of from which the control flows, this B3's P0 should also have the same value. That's the reason why I colored them with the same blue color, and it means that they should have the same number in the global value numbering optimization. Okay, so by replacing this computation into phinode, we can effectively reduce the number of arithmetic instructions that is involved in this computation. And yeah, and we can hope that it will actually improve the performance and energy efficiency by reducing a arithmetic instruction. And after that, all the uses of this B3's I0 is replaced with B3's P0, which is the new phinode that is inserted inside of this redundant computation. So okay, in the GVN we want to perform such an optimization as well. So when it is beneficial, we are going to actively introduce a phinode to reduce further computations like this. So far we saw 3 examples. The first example is local value numbering, which is easy, and we discussed that the control flow graph may complicate the algorithms, and this is such an example. We cannot replace registers with another when one is not dominating the other. And here's the more difficult and complicated example where we may want to insert phinode to further reduce the number of the arithmetic operations or computations. Okay, here are the examples we want to cover in this course, and here is an example basically. Here's an algorithm that explains what's going on in the GVN optimization at the higher level. So first of all, before delving into the explanation of the algorithm, we're going to define this set of numbers basically, and they are integers basically, but we are going to represent them or notate them with these circled numbers. So one circled is the number 1, 2 circled is number 2, and 3 circled is number 3. And in the execution of this GVN optimization algorithm, we are going to update the knowledge database. We already know about the computations. So there are two components in the knowledge database. The first one is register table, and the second is expression table. So for example, register table assigns registers with numbers. For example, we are going to say %v is numbered with 2. So such an information was used in the example 1 basically. And further, we are going to maintain what is called an expression table, which is also a constituent of knowledge database of the equations. So it is expressions that is the right-hand side of each instruction, but the operands are replaced with numbers when constant. So it is for example, we can say that number 2 plus 37 is numbered with 3 instead of %v plus 37 is numbered with 3 because it will represent a more general idea. The value that is represented by number 2 plus 37 is value that is represented as number 3. So after by scanning the blocks, by scanning the multiple blocks, we are effectively updating our knowledge database. We are going to update the register table and expression table by processing each instruction inside each block. And so far so good. And it already explains quite a lot about how to implement the local value numbering. But we are going to implement global value numbering, so we need to do a little bit more about the domination relation. And as in particular, we are going to maintain what is called a leader table. In the leader table, it is going to assign operand for each program counter or line number with a number, and it is assigned with an operand. So, for example, this entry means that at line 10 or at the program counter at line 10, we have leader value or canonical value for number 2, and number 2's canonical value at this L10 is line 10 is %v. So it means that at line 10, if an instruction or operand is numbered with number 2, then we can safely replace them with %v because %v is the leader value at the particular line for this particular number. So from now on, we can safely use %v in place of the values of number 2. So that's the meaning of this leader table. So here is an algorithm for manipulating these tables and actually scanning the blocks to deduce the replacement table. So first of all, the key idea, one of the key idea for this traversal is we use the reverse post order again. So recall that RPO is used in the register promotion optimization because it will greatly improve the the convergence. The time to converge in the recursive algorithm of the domination relation. And here we are going to use RPO in order to improve the compilation results. So using this RPO order, we can greatly improve the quality of the generated IR after this optimization because RPO help us to look at the blocks in the exactly needed way. So the meaning is that we are going to calculate the leader values, and it is beneficial to look for earlier blocks and deduce the leader values for these earlier blocks before those for the later blocks. And in the implementation of, in the complex contour graph, there may not be a canonical notion of earlier or later, but using this RPO, we can quite precisely mimic the actual order of computation inside a program. So that's the reason why we are going to use RPO in the scanning the blocks. And for each block, we are going to consider the phinodes and each instruction, and we're going to update the knowledge database that is consisting of register and expression tables, and also leader tables, because after in the course of scanning the blocks, we may be able to update the leader values. So for example, if you are going to compute a value with a new number, then you are going to add it to the leader table as well. So for example, the register table is, let's say that %v is defined, and it is computing a completely new computation. This computation, for example, 3 plus 8. Suppose this kind of computation hasn't appeared so far, and then we are going to assign a new number to this %v, and at the same time we are going to assign the leader table by saying that at this line the new number leader value is %v because it is just defined, and after this line %v should have been defined before. And if there were the leader value of the number of an instruction, then it means that the instruction can be replaced with the leader value. And we're going to add this information to the replacement dictionary. Oh, for example, %v is number with 2, and this number 2 has a leader value %w. Then we can safely conclude that %v can be replaced with %w because %w was the leader value. So this is basically the high level idea of these GVN algorithms, but we need to discuss a little bit more details about this. So in particular, we want to discuss how to actually update these tables for inside the block. And here is a more complete explanation of the algorithms. And for each block which is traversed in the RPO, and let's say that we are going to process a block B. And we need to initialize the leader table for the block B, right? And especially we want to get the leader table at the beginning of this block B. And this is the canonical choice for the leader table. The leader table at the beginning of this block B should be the leader table at the end of the immediate dominator of B. So at the immediate dominator of B, so suppose that some registers are defined at the end of this immediate dominator, then it will immediately mean that at the block B, all those registers are still defined, and we can safely use them. Why? Because immediate dominator of B is by definition dominating the block B. So every leader value that is valid in the final program counter of this dominator is still valid leader values at the beginning of this block B. So that's the meaning of this equation. And please look at this as an assignment instead of equality. So at the beginning, we are just going to copy and paste from the immediate dominators leader table. And in the remaining of this algorithm, we are actually going to update this leader table to get a better optimization results. And now, suppose we have a finode P, then we first see that all its arguments are numbered with the same number. And if it is so, let's say they are numbered with n, then we're going to say that, oh, this P should have the same value. So this is already appeared here. So this is numbered with 2. This is numbered with 2. And here, if there were a finode, then this and this have the same value, so same number. So the finode should have the same number too. So this is basically the meaning of this case. And otherwise, this finode is not analyzed well. So we are going to give a new number to this finode, which means that this is a new value and no existing computation have a syntactically equivalent computation with this new finode because the arguments are differing on the numbers. Okay, so far so good. So this is what is happening at the beginning of each block. And for each instruction and for each new finode, and we are going to update the leader table as follows. And suppose that we are going to define a register %i as some program counter. So when we are executing an instruction or a finode. And suppose that this %i is numbered with number n. It may be an existing number or it may be a new number, but regardless, let's assume that this I is numbered with n. Then we are going to do this. We are going to use and update the leader table as follows. So first of all, we are going to see whether there already exists a leader value for this. And if it is the case, then we are going to replace I with the leader value because I is apparently the redundant computation. And furthermore, at this point of time, at the time that I is defined, the leader value is already defined, and we can safely replace the new instruction I with the leader value here. Okay, so far so good. And the second case is dealing with such a case like example 3. So here, at this point of time, So number 2, for example, have the valid value for each predecessor. So this B1, which is a predecessor of this B3, this B1 have a valid leader for number 2. That is B1's I0. Similarly, in B2, this computation have a number. And the leader is B2's I0. And when we are going to deal with the instruction with the same number, we are looking for the leader value here, but there's none according to the we learned so far. But we're going to actually apply some optimization on the computation of this leader value. So at this point of time, we can say that, oh, when the control flows from this B1, we have a leader value, B1 size 0. And otherwise, if the control flows from this B2, then similarly, we are going to have a leader value, which is B2 size 0. And to sum up, if we use a phinode at this point of time, then we are going to have a leader value, which is this phinode of B1 size 0 and B2 size 0. And it is named with B3's P0. So that is basically explained here. So if the leader value exists for all predecessors, then we are going to create a new phinode. For example, the P0 in the previous example, and we are going to say the leader value will be the newly created phinode. And as a result, we can simply replace I with P, because P is before I obviously, and P is already numbered with the same number. So we can safely replace I with P in this case. So otherwise, these cases are for the cases where a leader value already existed, either directly or indirectly from the new phinodes. And otherwise, if there's no such an existing value with the same number, then we are going to just declare that the instruction or phinode just declared so far is the leader value at the time of this program counter, because it's a new value. No existing value had the same value, so that's the reason why we are going to execute this. Then if it is the case, then the leader table should be assigned with itself. Okay, this is basically the algorithms, and I'd like to conclude this video by looking at a simple example. What's going on for this GVN optimization for this simple example? So here we are going to calculate B equals A plus 1, and we're going to calculate B again here, and we're going to compute C using this B in calculating the same block. And in B2 we are going to calculate C, which is the same form with the C1, and B0 and B1 have the same form, and B3 should have the same form again. And C1, C2, C3 have the same form. And in B3, we're going to say we will compute the A plus 1, which is equivalent to B, and B plus 3, B plus 2, which is equivalent to C. And you can see that there are a lot of redundant computations. So A plus 1 is computed in 3 times in this program, and B plus 2 is defined in 3 times. So there are many computational redundancies. And the purpose of this GVN is reducing such redundancies. Now, here's an algorithm. We first calculate the reverse post order. It is B0, B1, B2, and B3. So far so good. It is roughly aligned with the order of execution. And for B0, we are going to process this instruction. B equals A plus 1. And let's say A is numbered with number 1, and we are going to process this instruction and say that, oh, number 1 plus constant 1 should be number 2, and B0 should have a number 2. And furthermore, at the end of this block 0, we are going to say, oh, in the leader table, number 1 should have a leader ampersand A, and number 2 should have the value ampersand B0. So the meaning of this is that at the end of block 0 here, at this point of time, when you meet a value with number 2, then you can safely replace it with B0. Because at this point of time, B0 is dominating the execution, the remaining execution. So on the other hand, 1 is also has the leader value A, which means that at this point of time, the values with number 1 should be replaced with, can be replaced with ampersand A, because ampersand A should dominate everything else. So far so good, and let's move on to B1. And recall that at B1, the initial leader table is the same with the final leader table of this B0. So this leader table is taken at the beginning of this B1. But the variable tables and expression tables are not changed. So it is only incremented. It is not decreased or changed. And let's process this block here. We are first calculating A plus 1, but they are already inside this knowledge database, and we can safely deduce that, oh, B1 is 2, number 2, because number 1 plus constant 1 is number 2, and B1 is calculated in such a way. So far, so good. And the leader value is not changed because B0 is already has a leader value, so we don't need to replace the leader value. Instead, we are going to say, oh, this B1 is redundant, and we can safely replace this B1 with B0. The reason is B0 is dominating B1. So in the same way, we are going to calculate the process each block, and we are going to assign a new number to C1, which is basically number 2 plus a constant 2. And we're going to say that the number 3 has a leader value, which is C1, which is defined here. And B2 is almost the same. So expression table and variable tables are updated. And for the leader table, it is taken from the final leader table of this B0 at the beginning of this B2. And after processing this instruction, we can see that the leader value of the number 3 should be ampersand C2. Because there's no leader value at the beginning of this B2, as 3 has no entry at the end of B0 in the leader table. But we're going to calculate C2 here, so C2 is becoming the leader value of this number 3. And let's move on to B3, where the beginning the initial leader table should be the final leader table of this B0, because we cannot reliably use the values defined here and here. The only values at this point of time, the only values that are reliably used is those defined in B0 or earlier. So as a result, the leader tables at the beginning of this B3 should be this. 1 is A and 2 is B0. Quite simple. And now, at this point of time, using this rule, this phynode rule, we are going to create a new phynode because the number 3 should have the leader value at the B3, but it doesn't exist in B0. But B1 and B2 have a leader value at the end of the block for the number 3. So if we create a new phynode, we can safely deduce that, oh, this new phynode, which is called this C5, has the same number as 3 in this case, and we can immediately declare that the leader value of this number 3 is C5. Okay, so far so good. And by scanning this block, we can see that number 2 and number 3 has already the leader values. So we can just say that the B3 should be replaced with the leader value B0, and C3 should be replaced with the leader value C5. That is just created a phynode. And using this analysis, we can do this. First, we need to insert a new phynode, which is used in this equation, and this C5 is actually used to replace C3, so we need to physically insert this C5 to the program. And that is the phynode of the leader values at the predecessors at the end of the block. So the leader value is C1 at the end of this B1 for number 3, and it is C2 for B2. And as a result, the C1 and C2 are placed in the phinodes arguments. And this C5 should have the same number, which is number 3. And yeah, that is basically the thing. And using this replacement table, B1, B3, C3 should be replaced with nope. They are just going away. It is not calculated afterwards. B1 is also not calculated. And as a result, B1 is replaced with this B0. B3 is replaced with B0. So B3 here becomes B0, and B1 here becomes B0. And C3 here should be replaced with C5. So that's basically the algorithm of this GVN for this example. So this is basically the last slide of GVN, and this is I hope this video explains the motivation and the algorithms and the example well, so that you can start working on your implementation of GVN in the KCC compiler. So if you have any questions, feel free to ask the questions in the issue tracker, so that we can immediately handle your question.